Okay, so in this video I'm going to look at Newton's approach to calculus, and I'm going to leave a lot out. I'm mostly going to concentrate on the fluxions. I'm not going to talk about this series or anything like that. Though I do think it's interesting to think about this series and just how he sort of saw series as a little more fundamental than we did. And we compute, if you think about the way that we compute series, it's all based very on calculus type methods, but he had very interesting ways for computing series, and I think it's a very cool idea to maybe just as a thought experiment or something like that, to think about how our calculus curriculum would look different if we sort of followed his development. I'm not saying that's something that we should do. I just think it's an interesting way to think about, and I just think it sort of shows that there are more ways, maybe even more ways that seem more fundamentally algebraic rather than calculus for dealing with power series. Anyways, but like I said, this is going to be on Newton's approach to the start of calculus, and I'm going to mostly work with his idea of fluxions and not mention power series at all. So, what is a fluxion? Well, he was he was not interested. In some ways, he was not interested in functions themselves, but as curves defined by relations. So for example, if we have a curve f of xy is equal to c, we know that in the xy plane, this is a set, the set of points that satisfy this relation will typically give a curve. Obviously if there's no points that satisfy it, then it's nothing, but typically what we get is a curve in the xy plane if we have a relation f of xy is equal to c. And what he wanted to think about, what Newton is thinking about, is always going to be motivated by motion. Okay, so the curve in the plane that is defined by f of xy is equal to c. What Newton wants to do is he wants to think about that as being the path that a particle travels, and at any point it is at x of t, y of t. So the coordinates x and y are actually, in Newton's conception, they are actually functions of t. They themselves are moving. And this is going to be something that will be pervasive in Newton's understanding of calculus. So a fluid is a quality that flows or that changes, and a fluxion is a rate of change. And it's denoted by either, that quantity with a dot above it, or that quantity, or x with a dot above it, or y with a dot above it. That's the notation that he used. Primes are also involved as well. And in addition to that, the dot notation is something that's still used today. So we haven't completely gone all the way with the Leibniz notation. These notations that Newton has are also, they get criticized a lot because they are a little bit heavy-handed in some ways and a little less clear about what's going on. The notations, when we get to Leibniz, we'll talk about this. Newton's notation is fine in some cases, but it's not as expressive as the Leibniz notation, which will be in another video, of course. So Newton basically has two goals. So given a fluid, he wants to find the fluxion. That is, if he knows the path of motion, he wants to be able to find the speed or the velocity of the particle going along that path. Would be like a physics rate of change way of pushing it or phrasing it. On the other hand, if he knows the fluxion at all times, he wants to know the distance traveled. Okay, so in other words, maybe saying that in language that we'd understand a little bit, given the position, he wants to be able to find velocity, and given velocity, he wants to be able to find position. Now, it's interesting, we sort of realize this nowadays after having gone through calculus as differentiation and integration, but really, remember that the way integration is typically taught is more fundamentally taught as is more fundamentally motivated, and really the definitions capture the idea that it's area under a curve, whereas it's really anti-differentiation what we're doing to go from a fluxion to fluid. So to go from velocity to position, what we're really doing is anti-differentiation. But the fundamental theorem of calculus connects these two ideas together of integration and anti-differentiation. That's why we sort of say integration when we mean anti-differentiation and things like that. And what Newton is going to do is he's actually going to connect the idea of moving quantities to be able to find areas under curves. So even in this conception of fluid and flowing and not immediately being things about areas under curves and stuff like that, he's still going to come up with a sort of fluid way of talking about areas under curves. Okay, so again, he uses the notation x dot. This means the same exact thing as dx over dt, at least in principle, but he doesn't use this notation. He doesn't use this as a ratio. And I think this is something that is kind of to his own loss. Now, I don't know if he didn't do it on purpose, out of spite or something, but it's simply works out a little bit better notationally to use dx dt. And we'll talk about this when we go to Leibniz. Okay, so for example, and we'll get to how he can compute these things in just a minute, but if x is equal to 3t squared, then x dot is equal to 6t. And so again, we're thinking about this as being a velocity and not a ratio, even though implicitly we can think about velocity as being a ratio, distance over time. Okay, so how can we compute with fluxions? So let me just give sort of a couple of examples of how we can do this. So O is going to be a small amount of time. In modern notation, we would probably call this delta t or something like that. So then if we have x, which we're thinking about this as being a function of t, that is, x is a fluid, it's a quantity that is changing with time, then x dot is going to be x of t plus O. So obviously, when I write it, my O's are going to look like zeros, divided by x of t divided by O. And this gives a rate of change. And again, we can already see similarities between this method and the method that Fermat was doing. In fact, the only difference in this method and the method that Fermat was doing is we're using an O here instead of an E. Okay, so for example, let's say x of t is equal to t squared. So, well, this is going to be very simple. This should be a very familiar computation. So let's just come up here and change it to x of t is equal to t squared. If we compute this ratio, just plugging things in, we're going to have t plus O squared minus t squared over O. Okay, now if we do some algebra up here, let's think about what's going to happen. When we FOIL this, or whatever you want to call it, we're going to have a t squared that cancels with that. We're going to have a 2ot, and then we're going to have a plus O squared, and we divide it by O. And now once we do a little bit of algebra, or I mean not a lot of algebra, we cancel the O there, the square there, we get 2t plus O. And now the idea is that O is smaller than any of the other quantities, so we just ignore it. And I'm not going to write equals, I'm going to write an arrow here, suggesting that they're not equals, but we transition to this, whoops. To get 2t. And so then if the fluent is t squared, then the fluxion is 2t. Okay? All right, so that, like I said, is a very familiar computation. That is exactly how we would compute the derivative in a calculus class using our modern definition, except, there's no limits here. We would obviously be doing everything with a limit and say, let O go to 0 or something like that. All right. I'm also skipping a little bit apart before this, where he has another way for sort of doing this with polynomials as well. Okay, so let's think about the product rule. We know what the product rule should be, right? So let's think about the product rule. So we've got z is equal to x times y. So let's compute the fluxion of z. So z dot. Okay, so what we're going to do is we're going to do x plus a little bit and y plus a little bit. So what I mean is the following. Z is going to be, z dot is going to be equal to, or let me do it like this first. Because I'm running out of room on my board here. So z dot is going to be equal to, let's see. Let me see if I can do this properly here. X plus x dot O. Okay, because this is like the change in we can think about this as being the new value of x. X changes from x to x dot o. I'm just going to make sure this is appearing nicely. Okay. X changes to x dot o. Remember, x dot is the velocity. So if we're at x and it's x is the fluid and x dot is the fluxion, then over a short time period of length o, x will change from x to x, x to x plus x dot o. Okay, all this is velocity times distance, velocity times time is equal to distance. And then similarly for y, we're going to have y plus y dot o. And now I think I'm going to run into trouble here. Maybe not. Okay, that looks like everything fits. And then we divide all of this by o. And again, we can see what's going to happen here. When we do some algebra, x times y is going to cancel with that x times y. And then so what we're going to have left is x y dot o plus x dot o times y plus o squared. And again, we divide this by o. After doing the appropriate cancellations here, we have x y dot plus x dot y plus o. And then again, this o is negligible, and so we forget about it. And now we have x y dot plus x dot y, which is of course the familiar product rule. Okay. So let's do one more of these. So let me. Oops. So there's multiple ways to do this next one. I'm going to do it one way, and you guys can maybe do it another way. Let's say that let's say z is equal to x squared, or this is equal to x times x. Then using the product rule that we just saw, it's going to be x times x dot plus x dot times x, and of course that's equal to 2x x dot. Okay, now here's where one thing that might be a little confusing to sort of translate into modern notation. This is treating x as a dependent variable, and then there's some other underlying variable t as an independent variable. So one way that they sort of got around this, or not really got around this, but they sort of, if you want to deal fundamentally with like y is equal to x squared and try to compute, y dot, like the fluxion relative to x. So we would here say, similar thing up here, y dot is equal to 2x x dot. To kind of make sense of this in a way that didn't sort of seem self-referential to have an x dot here, we would just say something like x is equal to t. So that x is kind of representing the time variable itself, and that x dot then would be equal to 1, and so y dot is equal to 2x. But again, even nowadays for modern notation, if you're dealing with partial differential equations and things like that, and so there's like many different types of differentiation going on, dots will typically mean differentiation with respect to time, or derivatives with respect to time. So this notation is something that has persisted to this day, and it's not honestly a little bit helpful because sometimes, again, if you're dealing in multivariable situations, we've got time as a variable and you've got space variables as well, it's helpful to have a separate notation that means something like differentiation just with respect to time. Okay. So how can you compute tangents with fluxions? Okay, because remember, one of the things that derivatives are supposed to do is supposed to give you the tangent of a line. So let's see. I'm going to try to draw, or the slope of the tangent line to a curve. So I'm going to try to draw a somewhat good diagram here. Already starting off kind of poorly, but let's say that's the x-axis, and the horizontal axis, the x-axis. And we have some curve like this, and we have the tangent line, let's say to this point. I'm going to try to draw it like this, coming down like that. Okay, so I'm going to call this y, and I'm going to call this x right here. So what we want to do then is, let's say this point here is x plus ox, and then this point on the curve here would be like x plus ox dot. This would be y plus, let me do this how I had it before, which I think was like this, and this would be y plus o y dot. Well, the idea is that these points, if you look at this triangle right here, the ratio I've run out of room here. The ratio of this side linked, this side, the triangle on this side and triangle on this side is going to be equal to y over x, which is the slope of the tangent line. So by similar triangles, the slope of the, by similar triangles, this triangle is similar to this triangle right here, which I haven't drawn very well, but this triangle is similar to this triangle right here. And what that tells us then is that the slope, since the slope of this line right here is y over x, is this, and that is the slope of the tangent line, is going to be this vertical component over that vertical component, again, by similar triangles. Well, what is the slope of this line? What is a ratio? So again, the slope of this line right here is that ratio, but it's the same line right there. So it's the same slope, and we have similar triangles, so the ratio of y over x is going to be the same as the ratio of that over that, but the ratio of y over x is the slope of this line, which is the tangent. So what we're going to have is y minus y, other way around. Well, it just depends on how you want to do it. Y minus y, so I'll keep it this way, I guess. Y dot O over x minus x plus x dot O. And again, after we do some simplification, we get y dot over x dot. Okay, well, what is y dot over x dot? If we have a function that's if this is a relation y is equal to f of x, then in the way that Newton might conceptualize it, it's y minus f of x equals 0. I see that I'm going off the screen now. So if this is y is equal to f of x, so if it's a graph of y equals f of x, then it is the same as y minus f of x is equal to 0. And again, conceptually, we're thinking about x and y as being fluents. That is, they're quantities that are changing. So what we have over here, y dot over x dot, if we simply take x dot to be equal to 1, that is, x is equal to t, then we get that the slope is equal to y dot, which again is exactly how we think about things in modern notation, or in modern ways of conceptualizing this. Okay. So we can also do integration as well. And again, as I mentioned before, integration is kind of a slightly overloaded term because of the fundamental theorem of calculus. So this was the other thing. So what we just talked about before was, given a fluent, how we can find the fluxion. Now what we want to do is, given a fluxion, that is, given a rate of change, how can we find the corresponding fluent? So this is essentially antiderivative. Okay, so for example, if we know that x dot is equal to t squared, and again, we're always going to assume here that x of 0 is equal to 0, just to make things a little bit easier here. If x dot is equal to t squared, then x must be equal to t cubed over 3. And then again, plus some constant here, right? Because this problem alone, if we know x dot is equal to t squared, of course we don't know what c is. But like I said, if we assume that x of 0 is equal to 0, then in this case, c here would also be equal to 0. And so this process, the way Newton has conceptualized it is very easy. If you know the velocity, that is, if you know the fluxion, then to find the corresponding fluent, all you do is just look for a function that look for a fluent whose fluxion is equal to the given thing that you have. And so if you're able to find one, great, that tells you what the fluent is. I do not know at which point it was seen necessary to prove that, okay, if you have two fluxions, then they're, the only fluents that have that as a fluxion are going to be, they are only going to be differing by a constant. Okay, in other words, certainly if this is the fluent, then that's going to be the fluxion, but I don't know how much they thought about if this is the fluxion, whether or not that's going to be the unique fluent, but it just sort of seems obvious. Okay, so how does he apply this to find areas? Okay. So essentially what we're going to think about is we're going to think about area. This is the x-axis, this is the y-axis. We're going to think about area itself as being a fluent. So you want to think about a curve, something like this. And this is going to be the point x of t, y of t. And then this area right here under the curve is going to be equal to a of t. Okay, so what can we do if we think about this in terms of fluent? So what we want to do is we want to be able to compute the fluent of A. So we want to be able to compute the fluent of A, and of course it depends on x and y. So let's think about what's going to happen here. This is I'm going to move this down. So the area A of t. This is a very common picture that you see in a calculus textbook, written, of course, maybe not in this notation, maybe with delta x's and things like that. So this is going to be x plus x dot O, and then we're going to have something like this. So this point is y plus y dot O. Okay, and what are we going to get when we try to compute the fluxion of A? So A, okay, so A dot is going to be the new value minus the old value. So A dot is going to be the new value minus the old value. Now, in this case, what are we thinking about as being the new value? Well, it's going to be whatever the value of this new curve is. So the area under the curve, and then this is the old value here. And so the new value, the new value minus the old value is basically going to be the area of this strip right here, because the new value is going to be the whole area, and the old value is just this area. And so the new area minus the old area is just going to be this area right there. Well, what that ends up being then, this strip right here is approximately, the area of that strip then is approximately, let me write it like this, is approximately going to be equal to that width there, which is x dot times O, times the height, which is y. Again, we're approximating this as a rectangle. And then we have to divide by O, and what we get is x dot times y, or maybe I'll write this as y times x dot. Okay, so what we know that a dot is equal to y times x dot. We don't care about a dot. we care about A. So how we translate this is we want to find a fluent whose fluxion is y times x dot. And I think there is a typo in the slide. It should, the dot there, there's a LaTeX error. The dot in the slide, let's see if I can point to it. That dot right there, if I'm pointing to the right thing, that dot should be on top of the x. Okay, so we want to find a fluent whose fluxion is y dot x. In other words, it's an antiderivative problem. Okay, it's a simple antiderivative problem. So what he's done is he has translated an integration problem, that is an area under the curve problem, to an anti-differentiation problem. Okay, now, in other words, this is just the fundamental theorem of calculus. Okay, but if you don't know what the fundamental theorem of calculus is, you have to sort of come up with it first, and that's exactly what he's done here. Okay, so as an example, let me just write this. So a dot is equal to y times x dot. And notice here, a of 0 is going to be equal to 0. If we start here, a of 0 is going to be equal to 0 because there's no area. Okay, again, if x of 0 and y of 0 both start here, then the area under the curve is 0. Really, we just need x of 0 to start over here. Anyways, let me just say that one more time. The reason that a of 0 is 0 is not because we're starting at the origin, but even if we had started up here, even if the graph had started up here, if x of 0 is at 0, there's still no area under the curve because it had, the point hasn't moved yet at time t is equal to 0. Okay, anyways, so if y is equal to x squared and x dot is equal to 1, so again, we're just sort of, conceptually, that's like identifying x with time. Then we have a dot is equal to y squared. Oh, sorry, y is equal to x squared. A dot is going to equal to x squared. And so now what we want to do is we want to find a fluxion whose fluent is y times x dot, where x dot is equal to 1. And then what we get here is that a is going to be equal to x cubed divided by 3. Again, we're just doing the antiderivative because, once again, if you look at this right here and compute its fluxion, you're going to get x squared times x dot, but if x dot is equal to 1, this gives us that. Okay, so the fact that we have two variables gives us 1 degree of freedom to pick what we want x to be. Okay, so this is the way that Newton was able to use his idea of fluxions, which involve motion, to be able to come up with a way to compute areas under curves, which is in some ways this very similar to what we're accustomed to, but in other ways it's a little bit different. So we sort of, when we teach this in calculus, we don't really make a distinction between these two different ways of thinking about it. We just sort of think about a lot of this as being different sides of the same coin, and it is, okay, but Newton and Leibniz both kind of conceptualize things a little bit differently, and because of that they were able to, and because they conceptualized things a little bit differently, they sort of came up with the same way, or very similar ways to solve the same problem, but got there in different ways. Okay, I think that's it. Yep, okay. So next up, I'm going to do a similar video for the Leibniz approach. It just so happens, so I don't listen to a lot of podcasts, but one of the podcasts I like to listen to is called The Rest is Science, and very recently an episode came out, and in it they're talking about infinities and stuff like that, and so calculus naturally comes up, and they talk a little bit about some of the battle and Newton's poor behavior in this dispute between Newton and Leibniz. And it's just interesting that now, at this time in history, we've gotten to the point where now people are more willing to publish things and sort of stake a claim to what they have discovered, rather than hiding their results and trying to use it as a way to weaponize and either defend their positions or to sort of go on offense and get other positions. So Newton definitely behaved poorly, but maybe there's some progress there. I don't know. I will let you guys be the judge.